All right, so chapter 8 is about estimating means and proportions. So starting off with 8.1, it says the assignment of a single value to a population parameter based on a value of the corresponding sample statistic is called an estimation. So I want to put a little note here. When we are unable to get the true data from a population, that means we have to get the info from samples and estimate. That's what this whole chapter is about. The reason why I wanted to kind of put this little note there is because this is really like mathy language, and I kind of wanted to put it in more of like English, what kind of made more sense. So that's what this is saying. So the values assigned to a population parameter based off of the value of the sample statistic are the estimate. We take our sample number that we get and we can estimate it, say that's what the population is going to be, which kind of makes sense. It's like if I want to hear what all statistics classes think, let's just say for example, I could just pull I can't ask everyone, that's just like too much. But if I just ask you guys, or just ask, like one person from each class, and then I can say, okay, this is what they think, I can generalize it to the whole population. So this sample statistic used to estimate the population is called the estimator. Two types of estimates are point and interval. A point estimate is the value of a sample statistic that is used to estimate a population parameter. The margin of error, which we're going to call E, just capital E, thankfully, like no fancy letters or anything like that, no Greek letters, just E, is the number we add or subtract from the point estimate. So if we have our point estimate in the middle, that's what we think it's going to be. But we have to have a little bit of wiggle room because we don't know for sure. So if we add a little bit of margin of error and subtract a little bit of margin of error, just like it does on Wiley Plus, saying if this is the exact answer, because of rounding, let's give you a little bit of wiggle room. That's what that margin of error is, that little bit of wiggle room that we can add to it to go a little bit higher and subtract to get a little bit lower. The point estimator of our sample, here are our symbols. The parameter for our population, here's our symbols, and there's an example. So for example, if we have X bar, that is our sample mean, which is estimating our mu, our population mean. So we know our sample mean is the same thing as our population mean. Same thing for proportions. For proportions, it's p hat for a sample, and it's p for a population. For variance, we use the symbol s squared, and then for a population, it's sigma squared, and the standard deviation is just s and sigma. So we use these sample estimators already to estimate what it would be for a whole population without asking the whole population. Remember, if we're using samples and sampling distributions, which we are in this case, then we'll use standard deviation from the sampling distribution. So if we have sampling distributions, we have to use this formula that we used in chapter 7. It might have been chapter 6. Anyways, whether it's 6 or 7, to find our standard deviation. So in interval estimation, an interval is constructed around the point estimate, and it is stated that it is likely that this interval is likely to contain a corresponding population parameter. So for example, just like we talked about earlier, we can have our point estimate, which is what we think that the answer is, but let's give us a little wiggle room. So let's add and subtract, adding to give you a little bit of higher wiggle room, subtracting to give you a little bit of lower wiggle room, and adding and subtracting that wiggle room, which is the error. So let's do an example. If the mean score on test 3 was an 80 and our wiggle room, our margin of error was 2.5, the confidence interval, the interval which would be likely to have our answer, would be 80, that test score, plus or minus our error, our 2.5, which would mean that it would be from 7.75 to 82.5. So that gives us a little bit of wiggle room to have that 80 in there. And then we can write this in interval notation as 77.5, comma 82.5. So those of you who did some type of algebra class before this, you know you've used interval notation a lot. And it says that it's from this point to this point. So that's what that interval notation says. So a confidence interval is constructed with regard to a specific confidence level, which is a percentage that corresponds to a particular z-value. So remember we talked about before our friend Chebby Cheb. Remember him? Or her? I don't know who, whatever they were. But remember that person? And we said that it was like 95% confident, you know, all that stuff. So we're going to use that same thing, kind of put it together with our z-values to see, okay, how confident are we that that actual population parameter, that actual data point lies within this interval? Are we 95% confident that it's in there? Are we 80% confident that it lies in there? How confident are we really that it lies within those two values? So like the previous example, how confident are we that that 80, even though they gave us that in the problem, lies within those 2 points? So that's kind of what it's saying. So the level states how much confidence we have that the interval we form contains the true answer, the true population parameter. So a confidence interval, which we label it usually as CI, just because we are efficient. Aaron, are you sticking with us, bud? So CI is a point estimate just like we did before, plus or minus that margin of error. So a lot of times we say that it's our point estimate, which is usually our X bar, plus or minus E, which is our error. And then remember we write that in interval notation. So our answer is going to look like our interval notation. So in parentheses and then plugging in our two numbers. So just like we talked about in empirical, remember we had like, it was 90, 95, and 99% like confidence. Those were the ones that we memorized or put on the formula sheet. It's the exact same thing. It's the exact same thing here. Commonly used confidence intervals are 90%, 95%, and 99%. Sorry, my brain's like 5 steps ahead. So to find these levels, the level is denoted by writing 1 minus, this is alpha. It's the lowercase Greek letter A times 100%. The confidence level is where alpha is the area under the curve. Outside the interval, which should contain the parameter, always give the positive value for z when using confidence levels. So what this is saying, in the middle we have 0. We have our negative z, we have our positive z. If this is our shaded region, if those are alpha, that means they're half. So this one would be alpha over 2, and this one would be alpha over 2. Together they make alpha. And then what's left over in the middle, that's going to be 1 minus our alpha. That's whatever's left over. No, the whole thing is 1. What's shaded is alpha, so whatever's left over is 1 minus alpha. So let's practice finding corresponding x values for the common confidence levels. We're going to find the desired z value based on the given confidence levels. So for example, for 95% confidence, we know that 1 minus alpha is going to be 0.90. So we need to draw this curve. So in the middle, we know in the middle is 1 minus alpha, which we know that's 0.90 because it told us. In the middle, we have 0. Over here is our negative z. Over here is our positive z. If we know 1 minus alpha is 0.90, that's telling us that alpha is 0.10. But if these are both alpha, that means this is alpha over 2. This is alpha over 2. So if alpha is 0.10, that's 0.10 divided by 2, which is 0.5. That's the area under the curve in the shaded region. It's going to be 0.5. Sorry, 0.05, yes, sorry. So we know half of alpha is on each side, so on each end it's going to be 0.5 because we know together that's going to be alpha, which is 0.10. So we know how to do this just from last test. We know how to find these z values. So in our calculator, we're trying to find the z value. So we know we can do second vars and then go down to the inverse norm to find our z value. We know the area under the curve is 0.05. And we're going to find this left one first. So if this area, it doesn't matter, these are the same exact number, one's positive, one's negative. So it doesn't matter, but I want to do what's easiest for me. And in the calculator, I know it does the area to the left. So if the area to the left is 0.5, we are good to go. So for everyone, it should look like this. And that will give us negative 1.64. So that means this one's negative 1.64, this one's positive 1.64. But we talked about it only says z equals. Up here it says always give the positive value of z when using confidence levels. So I'm just worried about z equals 1.64. So in our calculator, we did the inverse norm of 0.05. Talking about z, so it's normal, so our mean was 0 and our standard deviation was 1. So we're going to do the same thing now for 95% and for 99%. So if it's 95% of our whole thing, what's left over? I know 1 minus 0.95 will give us 0.05, so that's what's left over. And we know it's going to be the same thing on both tails, so we need to find divided by 2, so 0.05 divided by 2, which will give us 0.025. So now finding that z value, so in our calculator, inverse norm, or if you want to go to the z table, that's fine too, but I know a lot of us like to just do it in our calculator. Inverse norm, area to the left is 0.025. We are talking about z, so we know it's normal, so our mean is 0 and our standard deviation is 1. And we get negative 1.959. which we know is going to round up to 1.96. The reason why we're doing this now is because these z-values are common ones that we're going to use a lot. So last one, if we have 0.99, what's left over? Well, we know 1 minus 0.99 is 0.01, 0.01. Dividing that by 2 will give us 0.005. So our inverse norm, area to the left, 0.005, comma 0, comma 1. So same thing over and over and over. And we get negative 2.575. We want to use the positive version, so 2.58. So those are our most common z-values. I like everything to be super organized and like in one spot, not have to look for everything. So I thought it'd be helpful to make this table of the confidence levels that are super common that we use a lot and the z-values. So we're going to use this table quite a bit. For 90% confident, we found that it was 1.64. 95, we found it was 1.96. 96, we didn't find, but it's the same thing over. I went ahead and found it for you. 2.05. 97, same thing, 2.17. 98 is 2.33. We did find 99 right here, which is 2.58. So these are the most common ones. The 3 that we found are our top most common ones. But these are pretty common ones that I went ahead and found and put them in a table, so that way all I have to do is look at that one table. So questions, comments, concerns thus far? If not, let's keep going. So we really haven't got to the meat yet because we're still kind of just like getting introduced to this. So, go back. Stick with us, bud. Stick with us. Thank you. All right, so we have 3 different cases that we're going to look at. One is whenever we know our standard deviation, whenever we don't know it, and then we have to deal with proportions. So pretty much exactly like we did before. So for 8.2, interval estimations for a mean whenever our sigma is known. So we have 1 minus our sigma times 100%, which is our confidence interval for our population mean. Mu is found by our x bar plus or minus z times our sigma over the square root of n. This is our E, and you can see that right here. Our E is z times our sigma all over the square root of n. So we're just kind of taking it, what if they don't give us E? So that's how we would find E, because usually they don't give it to us. So our margin of error is the maximum error of the estimate, that is the quality subtracted and added from our statistic to obtain the confidence interval for the parameter. So E is that little bit of wiggle room. So we can find it by z times our sample standard deviation, which we know our sample standard deviation is our population standard deviation over the square root of n. So taking stuff that we did last time and just adding that little piece to it. So let's finally get to an example. It says a sample size of n equals 25. The mean price of a book is x bar equals 145. The population standard deviation is known to be $35. Part A says find the point estimate for the mean of the population mu. Well, we know mu is the same thing as our x bar, which is 145. B is what is the margin of error. To find the margin of error, we first have to find our sampling distribution, our sampling standard deviation, which is our standard deviation over the square root of n. So our standard deviation is 35 over the square root of n, which is 25. So just plugging into all these formulas. Bingo, 7. Yep, you're right. Thank you. 35 over the square root of 25, which is 35 over 5, which is 7. So second, for a 95% confidence interval, 95 confidence level, our z, going back to that table that we just did, 95%, so our z value is 1.96. So that tells us which one to use. So that means our E is our Z times our sampling standard deviation. So 1.96 times 7. So our margin of error is 13.72. This one, right, that's from the table on the previous page. That way whenever you go home and you're like, where did we get that number? That's how you knew. How we just pulled it out of thin air. So that's kind of like the new part that we're doing. So last but not least, part C says construct a 95% confidence interval for a population mean. So we know that it's our x bar, which is 145, plus or minus our error, which is E, which is 13.72. So we know we're going to have our 145 minus that 1372, comma our 145 plus that 13.72 to give us that little bit of wiggle room on both ends. 145 minus 13.72 will give us 131.28, and 145 plus 13.72 will give us the upper bound of 158.72. So that is our confidence interval. We are 95% confident that if we were to take all of these population of textbooks, that the mean would be in between those two numbers. We don't know what the population is because we only took a sample and only took 25 out of all of them. So it means that we're 95% sure that the mean price of a book will be between $131.28 and $158.72 based off of this sample data. So that was for 95% confident. Let's do the same thing for 90% confident. This time, if we're 90% confident, we have a different z value. 90% means our z is 1.64. That's from the table on the previous page. Find the margin of error, which is taking that z value of 1.64 and multiplying it by our sampling standard deviation, which we found up here to be 7. It's still all the same data, so it's still going to be 7. So 1.64 times 7, which is 11.48. What do you notice about this margin of error compared to the previous margin of error? It's smaller. And when you think about it, okay, so here we're going from 95% confident, we're going to be less confident. From 95 to 90, we're going to be less confident. So if we're less confident, I can kind of zero in. If I have a super broad interval, that means I'm pretty sure that it's going to be in there. But if I have a smaller interval, that means I'm less confident that answer is actually going to be in there. Are we good with that? That's what we're going to say in 1 second. So using this new margin of error, construct a 90% confidence interval. So our x bar, which is 145, plus or minus our new error, which is 1148. So that will give us 145 minus 11.48, comma 145 plus 11.48. And that will give us this interval from 133.52 to 156.48. We're narrowing in our interval, which means we're less confident. If I were to hit a ball, if I were to throw a ball at a target, you know, in the middle, whenever it's like a super, like a darts, I'm not very good at darts, obviously. I feel like that's my personality, probably obvious that I'm not good at darts. But okay, so you know on the outside how you have like less points because you have more of an area to get in, but in the middle where it's like super hard, so it's only one little spot, that's where your most points are because you're less likely to hit that. So it's the exact same thing here. If you're zeroing in and getting a smaller interval, a smaller space to hit, you're going to be less confident. So the true mean may or may not actually lie in this interval because it's only 90% confident. So we're not 100% confident, and it's okay. That doesn't matter. But when sigma is known, how can a researcher control the width of this confidence interval? How can we control how wide and how spaced out it is? So we could use the value of z, which depends on the confidence level and by using the sample size. Which makes sense too, because if I were to throw that dart 100 times, I'm more likely to hit something than I am if I only were to throw it 5 times. So the more times I throw it, the more likely I am to hit it. So same thing here. The more data I collect, the more likely I am to be accurate. So if we have a smaller confidence level, that's going to be a smaller interval. And the larger sample size let's put here less confident. And that's going to be a smaller interval. So those are ways we can really zero in our answer. I also want to put a note here that our margin of error our E value decreases when we are less confident. Our confidence level decreases. Which is pretty much what this is saying. I just wanted to kind of put on paper what I keep blabbing about, so that way you kind of remember it, because this is all going to come back. As you're copying this down, any other questions, comments, concerns that you have for me so far? All right, so if we're good, let's keep going. So I kind of rewrote this out. I just wanted to put it on that same page that we talked about, but the lower the confidence level reduces the width of the confidence interval, which is what we said over here. If we're less confident,
you get a lower result.
Yeah, you get a different result. You get a smaller interval. And then a larger sample size n will give us a smaller interval as well. And that's what the second bullet or whatever star is saying. Increasing the sample size will reduce the width of the confidence interval. The width meaning how wide or how big our confidence interval is. Determining the sample size when estimating the mean to get the desired margin of error. So meaning if they say that you want your margin of error to be this, how could we get that? So we can figure out what our n value should be. Remember, whenever we talked about n, just like before, always round up. No matter what our rounding rules say, you always go up to the next number. So for example, if I'm saying like 7.1, that will even round up to 8. You always just go up to the next number. And it is always a whole number. Because this will be like, how many people do you ask? You can't ask 0.1 of a person. And then here is the formula that we're going to use for that. N equals z squared over sigma times sigma squared all over our e squared. So let's use this in an example. For a population data set, our sigma is 12.5. How large a sample should be selected, so what's our n value, so that the margin of error of estimate for a 99 confidence interval for mu is 2.50. So they tell us our sigma is 12.5. We know our margin of error, our e, so the margin of error is 2.50. We know we want to be 99% confident. So that's telling us our z value, going back to this table, should be 2.58. So we don't know our n value. What is our n value? So if we have n equals z squared times sigma squared all over e squared, just plugging in our values. So z, we know, is 2.58. Our sigma is 12.5. All over our e is 2.50. So just plugging in to this formula. Plugging this into our calculator, 2.58 squared times 12.5 squared divided by 2.50 squared will give us n equals 166.41. But remember, no matter what, always round up to the next whole number. So n equals 167. So we should sample 167 people or things or whatever. Our sample should be 167 to get that 2.5 margin of error with a 99% confidence level. Always round up to the next whole number. Questions, comments, concerns on number 1? Example number 1. If not, example number 2, a bank manager wants to know the mean amount of mortgage paid per month by homeowners in the area. A random sample of 114 homeowners showed they paid an average of $1,573 per month for their mortgages. The population standard deviation is 209. Part A says find the 99% confidence interval for the mean amount of mortgage paid per month. What just happened? All right, let's kind of just put down what all we know first. So we know it's 114 homeowners. So N equals 114. We know that the mean, the average, is going to be our X bar, which is 1573. It told us the standard deviation is 209. It told us that we're 99% confident, which going to our Z table, 99% confident means that Z is 2.58. And then we're looking for the confidence interval. So to find that confidence interval, we have to do our X bar plus or minus our error. Our error is X bar plus or minus Z times the sampling standard deviation. This is just from the previous page. Our sampling standard deviation, we know, is our population standard deviation over the square root of n. So now we use this and we can plug all this stuff in here. So X bar is 1573 plus or minus Z is 2.58 times our 209 over the square root of 114. Here's the thing. Whenever you plug this into your calculator, this is going to be a super ugly number, but I don't want to round it because then whenever I round it, it's going to kind of round everything. So what I want to do is, in my calculator, do 1573 minus 2.58 times 209 over the square root of 114, comma 1573 plus 2.58 times 209 over the square root of 114. So I'm subtracting to get the lower bound, and I'm adding to get the upper bound. The lower limit, the lower number, and the higher number. Whenever I plug this into my calculator, though, we can use this efficiently and just plug it in once. So I'm going to show you how to do that.
I do have a question.
Yes, please.
Why did you do the X bar plus or minus E? Like, why did you write all those other
Steps?
And
Yeah.
we're only doing
The last one.
The last one.
Great question. Honestly,
I know you're extra, so tell me.
yes,
why
no,
you did
I'm very
that.
extra. Okay, so going back, we talked everything so far. Here's my first page. About it being our X bar plus or minus E. Before they gave us E, we didn't know E. So then we kind of took it, we just kind of did like baby steps along the way. We took it and found that E was this formula. And it's just kind of like, and then we took this formula, we made it to this formula. So honestly,
E equals, okay.
yeah, they all kind of equal each other. Honestly, this is the only one that I use. But here's the thing. Sometimes if they give you the error, you don't have, it's kind of like you use whatever they give you. So I knew that we started off here, and then I didn't have the error, so I had to find the error. So I plugged this formula in for our error. Well, I didn't have our sampling standard deviation, so I had to plug in my formula for sampling standard deviation.
But they gave us all those numbers. So in general, if they didn't give us that, we would have to do all those steps before. If they didn't give us all of that information.
Well, if they didn't give us all this till they gave us the error, I could just plug it into this first one and not have to do anything else. But this is like our formula to
Like
find.
If they were asking for the error, you would do step one.
Yes,
And then
yes.
if they were asking for step two, would be.
If they gave you the sampling standard deviation instead of the population standard deviation, you could just stop here.
Okay. All right. Okay.
Yeah. No, that's a great question. honestly, and I kind of pointed at the wrong thing, but this is the main thing that I use. And honestly, I would probably only write this just for our note's sake. I wanted to show you where I got that from. And I know that the error is this formula. Okay, and then I know that our sampling standard deviation is this formula. So it's kind of like I had to substitute until I could plug it into my formula.
Gotcha.
Like we had to plug in formulas into our formula. Does that make sense? On the formula sheet, so this is the formula sheet, and this is just from the book, so that's what I have to give you is what's from the book. See, like, for example, they give you that here's our confidence interval, which is this formula right here. And they tell you where X bar is this. Well, I don't want to plug in this piece and then plug in this piece. Like, I just want to plug everything into one organized formula. So honestly, I don't really like the way that this looks. But they're wanting you to take this and plug it in here. And that's what we did. So we just kind of put it together in one big formula, if that makes sense. No.
No, it's okay. It's fine. I just wanted, like,
You were, yeah, like, why are you
I knew
doing that?
that you needed the confidence intervals, so it was just kind of like, so.
So you just went straight to this
formula.
point.
Just give me that one form.
Yeah, so, yeah.
And then that's what it just kind of threw me. So should we do that every time,
No.
just like you did?
No, and that's totally okay. But on the formula sheet, it doesn't give you this one formula.
Okay.
So I'm trying to maybe like teach you if you just know this formula, you just use that and you're good. But if you don't know it and you need the formula sheet to help you remember it, that's how you would get to that formula. Maybe that's a better way to explain it.
Okay.
Which is like dumb because like they give you the formula sheet. Why don't they just give you what you need and take out everything else? But that would be too easy. I don't know. Thank you so much for asking a question, though. All right, so let's plug all of this mess into our calculator. So 1573 minus, exactly like I see it, 2.58 in parentheses times 209 divided by the square root. Our square root, by the way, is hitting our second button and then x squared, kind of like diagonal to our 7. And it's 114. So scroll out. So that will equal 1522.497, which will be 50.
So 1523.
Well, this one we're not looking for n's. We don't want to round this one up. We want to round this one normal. We only round it up whenever we're looking for n. So thank you for bringing that up. And then now I'm going to do the exact same thing, but I want to change that minus for a plus. So instead of taking the time to rewrite everything, I'm just going to hit second enter, and it'll bring me back whatever I previously entered, my entry, and then just scroll over, changing that minus to a plus. And that will give us our upper boundary, 1522.497. I didn't even do it. What the heck?
1623.5.
Thank you. I'll make sure you're paying attention. You passed. Passed the test. 1623. .50. And that's our answer. Now, there's a pretty big gap here from 1522 to 1623. That's a pretty big gap. So if this was too wide, how could I like narrow it down so that way I knew a little bit more precise what our population parameter was, what our actual mean was? So we have a couple of different things that we talked about on the previous page. But one, we could increase the sample size. The more things that we look at, the more accurate we're going to be. Just like the more darts I throw to the board, one of them's got to stick eventually, hopefully. So increase the sample size n, or if you want to get more honed in, I could just say, okay, I can hone it in more, but I'm not going to be as confident if I do so. So we can also lower the confidence level. Here we were 99% confident. That's pretty certain. So if we're that confident, I want to have enough wiggle room that if I make a little error, it's going to be okay. But if I have less confidence, I can be a little bit more exact. So just a little side note down here. The way they word it sometimes, I wanted to make sure that you've seen this wording. As n increases, n remembers the sample size, the interval decreases, our interval gets smaller, gets more precise. Likewise, as the confidence decreases, which is exactly what we said up here. I just wanted to show you this wording because I don't like, sometimes they word it too mathy. As the confidence decreases, the interval gets more precise. The interval decreases. And the same thing the other way around. So it could be vice versa. Or vice versa, whatever it's called. Vice versa. That's a weird word, vice versa. The other way around, whatever. Before we go on to example 3, questions, comments, concerns so far? We have 2 more examples from this type. Remember we talked about 3 types. This is our first type, where they give us our sigma, our standard deviation. All right, let's keep rolling then. Page 5, number 3. A standard deviation for a population, our sigma value is 7.42. A random sample from this population gave a mean equal to 48.37. Determine or construct a 95% confidence interval for mu, assuming that n is 196. So let's write down everything they told us. They told us our sigma, our standard deviation, is 7.42. Our x bar, they told us, is 48.37. They told us we were 95% confident. So going back to our z table, that's telling us that our z value is 1.96. And they told us n is 196. So yeah, let's just use that formula that we know we're going to use. X bar plus or minus z times our standard deviation over the square root of n. Let's just get to the point. Plugging in everything that we know x bar is 48.37 plus or minus our z we know is 1.96 times our standard deviation, which is 7.42 over the square root of 196. So just like before, I want to find that lower boundary by subtracting our error and find the upper boundary by adding our error. Remember, this is our error. That is our margin of error. So we have 48.37 minus that stuff, 1.96 times 7.42 over the square root of 196, comma 48.37 plus that stuff, plus 1.96 times 7.42 over the square root of 196. So plugging it into our calculator. Scroll it over to get out. So our lower limit is going to be 47.33. Doing second enter, and then scrolling over and changing that minus, this time actually changing it to a plus, will give us the upper boundary of 49.41. And that's it for example 3. We're going to do one more like this. And then we're going to go on to the next thing, the next topic. Before we go on to example 4, questions, comments, concerns on example 3. So example 4, a city planner wants to estimate the average monthly water usage. He selects 40 households, which give a mean usage of 3,406.80 gallons over a 1-month period. Based on earlier data, the population standard deviation of monthly water usage is 387.30 gallons, making 97% confidence interval. So again, writing everything that they gave us. Selects 40 households, so N is 40. Mean water usage, so that way our mean, our X bar, is 3406.80. The population standard deviation, so our sigma, is 387.30. And we are 97% confident. So using our confidence level thing here, 97 would be 2.17. So let's use our formula, X bar plus or minus our error, which is Z times our standard deviation over the square root of N. So again, remember this is our error. So plugging in everything, so 3406.80 plus or minus Z, which is 2.17, times 387.30 over the square root of 40. So we need to do plus and minus our error to give ourselves a confidence interval with that little bit of wiggle room. So we have 3406.80 minus our error, so minus 2.17 times 307.30 over the square root of 40, comma 3406.80 plus our error, so plus 217 times 387.30 all over the square root of 40. Do you hear someone screaming? Yeah, did you hear that? Okay, thank you. I'm not crazy, but I hope everyone's okay. But it's kind of like a weird sound, right? Maybe some risky business is going on in the bathroom. It kind of is what it sounds like, doesn't it?
Or someone got a jump scare.
Maybe.
It happens. Like last week, it kept walking
Yeah,
by
let's-
and I should pop out of nowhere.
Yeah. Let's not get scared again. Anyways, what is up with this Monday nights being scary? All right, let's keep going. Plugging this into our calculator before we get scared. So plugging it in exactly like we see. I mean, I just wonder if we should go check on it, but I don't even know where this noise is coming from. Is everything okay? Like in the hallway, we were hearing weird noises.
I did.
Were you in the bathroom? Was everything okay?
Yes, ma'am.
And everything was okay?
Yeah. Yeah.
Okay, well, hopefully we're just.
Weren't screaming in there.
Yeah. Yeah.
Yeah.
Yeah, it wasn't you, was it? I guess everyone's fine. Whatever. Hopefully.
There were noises?
Yeah, I don't know. Like I feel like it's coming like either through the walls or like the ductwork or something.
I heard it behind me.
Oh, that's even scarier.
Like,
Oh gosh.
Like not like right behind me, but like coming from over here.
Yeah, like I think the ductwork is really weird where it like echoes. So like I know that sounds weird only because this has happened before. And people actually it was your cousins and your brother and your cousin. Yeah. Well we were like, what the heck is that noise? And they were watching a soccer game or something.
Oh
In the like the other room, like all the way at the end.
my.
And we're like, what is that noise? Like, is everyone okay? Like, we were doing the same thing. And it was them, and it was traveling through. And they're like, what's wrong? Because I went in, I'm like, what are you guys doing? Are you okay? Like, yeah. It was funny. Anyways. So maybe it's just something like that. All right, so our lower limit is 3,273.91. And then doing second enter. Oops, that's not second enter. Second enter. And then scrolling over to change that minus to a plus will give us our upper boundary. 3539.69. Is your brother freaking out about being hurt? Is that your brother, right?
Yeah, one of them is.
Yeah.
I don't know.
I hope that he's okay.
Go check it out.
Yeah, be careful out there, Nick. Be careful. I'm going to ask security if there's like a weird class or something going on at this time. Because I don't hear it during other classes. Anyways, last call. Questions on number 4. So that's our answer. 3273.91 to 3539.69. So basically, it's all just plugging in that same formula. So we're not too terrible yet. Let's keep going. So our next little topic that we're talking about is 8.3, which is interval estimation whenever sigma is unknown. So remember, 8.2 is about whenever we knew sigma. This is about when sigma is unknown. And instead, the sample standard deviation is given or calculated. For the samples where the population is approximately normal and the standard deviation is not known, we are going to use the t distribution. So meaning, instead of having z values and z tables and z stuff, we're going to have t's. This is like more likely in a real life scenario. In real life scenario, you're not going to have the population standard deviation because that means you have to have everyone's data. So it's going to be most applicable to real world situations. Oh, that was stupid. I just blew like trying to blow this thing with my mask on. It's like, it didn't go anywhere. I'm like, what the heck?
That works well.
That's funny. Our problems these days. All right, so the distribution has one parameter, and it's called our degrees of freedom. And we label it as DF, which is totally dependent on the sample size. So our degrees of freedom is n minus 1, and then this is when our mu is 0. So just like when we had z, and we made it to z, we normalized it, and our mean was 0, standard deviation is 1, same exact concept here. All right, so to find the t value from the distribution t table, which I'll talk about in 1 second, make a confidence level of decimal, so move our decimal 2 places to the left. Use 0.5 minus our confidence level over 2 as an area. And then find our degree of freedom, which is n minus 1. This time our margin of error, before remember it was z times our standard deviation. Now we don't have z, we have t. This time we don't have a standard deviation. So we're going to use s sub x bar. So our confidence interval is our x bar plus or minus our error. And then where same thing, where our error, where our sampling standard deviation is s over the square root of n. So moral of the story, like we talked about earlier, this is just a lot to get to one problem. So our main formula is x bar plus or minus t times s over the square root of n. This is the formula that kind of puts it all together, which is just like the formula that we used previously, just when t's and x's, exactly. All right, so for when n is 25, x bar is 186, s is 12, and the confidence level desired is 95%, construct a confidence interval for the mean. So first it kind of walks us through our steps. Like the first example, they just kind of walk you through step by step. Find our sampling standard deviation, just like we did before, but this time we have s, because s is for our sample, over the square root of n, so 12, over the square root of 25, (2.4). Next, in order to find t on the t table, we have to find our degrees of freedom. Our degrees of freedom are n minus 1, so 25 minus 1, which is 24. And this is going to be the left column. Of our t table. Now, if you don't have a t table, if you forget a t table, or whatever your case may be, this is on Blackboard under test 4. So that way, if you need to print another one or whatever. So 24 is the degrees of freedom. Find the area in each tail, which was that formula right here. So 0.5 minus our confidence level, which is 95%, which in decimal form is 0.95, moving that decimal 2 places to the left, divided by 2. So 0.5 minus 0.95 divided by 2, and that will give us 0.025. And this is going to be the top row of our t table. So we need that degrees of freedom, which is 24. Then we need that top row. So now going to our T table. Notice it's two-sided. So looking at our degrees of freedom, which is our DF, going down to 24. And then we have our area under the right tail, which we found was 0.025. So 0.025, where these two things meet, will give us
2.064.
2.064. Bingo. So 24 degrees of freedom. And then 0.025 will give us this 2.064. And now it's exactly like Z, but now we just have T. So that means our error is T times our S over the square root of N. Or our error is T times S of X bar, which we already found, so that's why I didn't want to do it the long way. So our T is 2.064 times our 2.4, which we found in part A. 2.064 times 2.4, which will give us 4.9536. So our confidence interval is X bar plus or minus our error. So X bar, which is 186, plus or minus our error, which is 4.9536. So our interval is 186 minus 4.9536, comma 186 plus 4.9536. So same exact thing. The only thing that was different was instead of looking at that table for our Z value, we looked at our T table for our T value. Because they didn't tell us our standard deviation, so we had to find it another way. That's why we can't use Z. So plugging this into our calculator, 186 minus 4.9536, and second enter, 186 plus 4.9536, which will give us our upper and our lower bounds. So our interval is 181.0464, comma 190.9536. And then we can round however Wiley Plus tells us to round. Or the test can be multiple choice, so however the test multiple choice rounds. And that's page 6. We're going to do another example next, using the same data to find another confidence interval. Before we go there, questions, comments, concerns from me, please. All right, so it says construct a 99% confidence interval for the same data that we did on the previous page. So on the previous example down here, we found that our standard deviation was 2.4, so we're going to use that, 2.4. And that was from the previous page, same as the previous example. For our t value, so we are looking for the area, going to our t table. It's looking for the area and the right tail under the curve. So we're looking for the area, which is always 0.5 minus 0.99 all over 2 because we have a 99% confidence interval. So 0.5 minus 0.99 divided by 2. Oops. And that will give us 0.005. So that's the area we're going to use on our t-table. And we have our degrees of freedom, which is n minus 1. So if you go to the previous page, our n value was 25. So we have 25 minus 1, which is 24. So we're looking at, on our t-table, 24 degrees of freedom. So looking at 24, going over to 0.005, which is right here, and we get 2.797. Are we okay with our t-table? Just like our z-table, same concept, 2.797. So now we need to find our error. Remember, our error is t times s sub x bar. So we have our 2.797 times our standard deviation for our sampling distribution, which is 2.4. And we will get our error is 6.7128. So now remember, this is all just getting us ready to find the confidence interval. The question asks us to find the confidence interval. So our confidence interval is x bar plus or minus our error. Our x bar from the previous page was 186. So 186 plus or minus our error, which we just found was 6.7128. So we have 186 minus 6.7128, comma 186 plus 6.7128. Now I want to make sure, because I answered some email questions over the weekend, and I want to make sure to really drive this home, because that was a question for multiple people. Make sure this is interval notation, so it has to go from least to greatest. It has to go from left to right whenever we look at it. So it has to be in the right order, from least to greatest. So 186 minus 6.7128, and second enter will give us our entry, scrolling over and doing plus. So that will give us our answer of 179.287 and 192.7128. Again, we would just round as needed, but I don't like to round. I'm going to leave it as much as I can. So questions, comments, concerns for this one?
Just let me try to get all that.
Okay. Stay with us, that way we don't have to wait. All right, so next example, find the t value for t with a sample size of 14, so our n value is 14. And the area in the left tail, so left is telling us that our t value is going to be negative, is equal to 0.025. So if we know n is 14, we know our degrees of freedom for our t-table is n minus 1. So 14 minus 1. And we know the area under the curve they gave us was 0.025. So giving you a second here, then we're going to go to our t-table. Our area under the curve is 0.025. Our degrees of freedom is 13, so finding where these two things meet, we get 2.160. Remember, this tells us the right tail, so it's the right side of 0. So it's going to be symmetric, the same thing on the other side, but because it's a left tail, we have to say it's negative. So t is negative 2.160. Boom, done. We don't have to do the confidence interval here, just find t. So giving you a second to copy this down. Questions, comments, concerns on this example. So we have one more of these because I feel like this, I really wanted to make sure that we understood this part. So find the value for t with a sample size of 22. So we know n is 22. So we know our degrees of freedom is n minus 1. So 22 minus 1, which is 21. And the area in the right tail, so we know t is positive. And our area is 0.10. So our area under the curve is 0.10. So give you a second to write that one. And then we're going to use the same information and go to our t table. Is that my computer? I never heard that sound before. All right, so going to our t table. So our area is 0.10, so we know we're going to be in this first column. And then our degrees of freedom was 21. So where these two values meet, we get 1.323. It was talking about the right tail, so we know t is positive. So boom, that is our answer. That's our t value. T equals 1.323. Again, how could I help you understand this? Because we're going to use this skill and just add to it. So questions on this one? If not, let's keep going. So it gives us a sample of 6 observations taken from a normally distributed population, produce the following data, rounded 3 decimal places, so it tells us that. Here's our list. So it tells us a sample of 6 observations. So we know that n is 6. We have 24.7, 21.3, 25.4, 22.6, 23.7, and 25.2. And it asks us part A, what is the point estimate of mu? What is our sample mean? So we know mu is the same thing as x bar, which is our mean. So that means we can add it all up and divide by 2. But we have a calculator. So let's use our calculator. So, okay, let's kind of do old school stuff, but you can see both ways. So let's do 24.7 plus 21.3 plus 25.4 plus 22.6 plus 23.7 plus 25.2. Just adding them all up. And we know we are going to divide by the number there are. There are 6 things, so divided by 6. Boom, that gives us 28.1866, which rounds up because it's 3 decimal places to 23.817. Boom, that's our answer. So we added up and we divided by 6, which is our n value. That's old school, which is totally fine. I'm all for old school. Say we want to be fancy. Say we forget to do that. We can also plug it into our calculator like we did on test 1. Are we ready to go there? Sure. So going to our stat button, we want to go to edit, so we're there. And I want to plug this into O1. So I just want to erase everything, so I like to start off with a clean slate. And we're going to type in our list. So 24.7, 21.3, 25.4, 22.6, 23.7, oops, 25.4, 22.6, 23.7, 25.2. So in our calculator, We went to Stat, then we went to Edit, then we went to List 1. So now we're going to go back to our Stat button. We're going to go over to Calculate this time. And then we're going to go to one variable stats like we did before. This time we don't have a frequency, we just have L1. Oops, so I want to clear out my frequency. Or if you have an older calculator, make sure you put L1. Boom, we have the same thing. X bar is 23.817. So whether you let the calculator do the math for you or whether you just plug it into your calculator because it's not that bad of a formula, either way, you get the same thing. So questions, comments, concerns on this one? All right, so let's make the 90% confidence interval. So we need to find the area under the curve. So to do that, our area under the curve, remember it's 1 minus our sigma over 2. So let me write over here, area under curve. So we have 1 minus 0.90 over 2, which we can plug into our calculator. I'm sorry, this is 0.5 minus. So 0.5 minus, notice I put this in parentheses. Parentheses will never hurt you. So if you're unsure, go ahead and put them there. I like whenever we have a fraction, parentheses just means grouping it from something else. So I always like to put fractions in parentheses. And we get 0.5. So that's what we're going to use on our t table. 0.05. So we have our area, our degrees of freedom, n minus 1, so 6 minus 1, which is 5. So we have the two things that we need for our t table, our t value, which is what we did on the previous two problems. So we should be really good at finding the t value. Before I go to the t table, I'll give you a second to write all that out. All right, so our degrees of freedom is 5. Going over our area is 0.05. So boom, we get our t score, t value of 2.015. So t equals 2.015. All right, so remember our whole point here was to find that confidence interval. For our confidence interval, we need x bar plus or minus t times our sampling standard deviation, s of x bar, which we know s of x bar is s over the square root of n. So x bar plus or minus t times s over the square root of n. Our x bar we found right here was 23.817. plus or minus our t we just found was 2.015. Our s we're going to find in our calculator. So whenever give you a second to finish writing this, I'm going to go back to the calculator. This is where that putting it into the list helps, because now whenever we go back to stat, go back to calculate, go back to one variable statistics, we are looking for our sampling standard deviation, our S, which is 1.6142. So that's what we're going to use, 1.6142, and this was found as S sub x on one variable stats all over the square root of n. We know n is 6. So we can plug this right in to our calculator. So it wasn't my computer that was acting funny. It was your computer.
Actually, that's my phone.
Oh, it was your phone. Even better.
We got to silence it.
No, you're fine. I was just making sure. I never heard that. I thought it was my computer for some reason. All right, so we have the negative version to give us our lower boundary. Remember, just like on test, I think it was test 2, lower boundary, upper boundary, same concept. This is our lower boundary. And then we have our upper boundary, which is the positive version. Ugh. That stuff. Dot, dot, dot. All right, so 23.817 minus 2.015, our t value times that sampling standard deviation. Which will give us the lower boundary of 22.4, said round through 3 decimal places. So 891 will just be 89. Second, enter, scrolling over, changing that negative, that subtraction to addition. Our upper boundary is 25.1448. We'll round up to 5. And boom, that's our final answer. So kind of putting everything together for one problem. And there's quite a few. This is of this, like putting it together for our confidence interval problems on the homework. So I wanted to make sure we were okay with that. So we have one more page, I believe, for chapter 8. Nope, 2 more.
Yeah.
For chapter 8. Oops, there it is. So before we go there, questions, comments, concerns for me? How could I help you understand this better? So remember, before we go to the next problem, we use T whenever we don't know the population standard deviation. We only know the sample standard deviation. That's whenever we know to use T. Whenever we do know it, that's whenever we would use our Z value. So be very careful with the wording. If it's talking about the sample and it gives you the standard deviation with the sample, that's whenever you use T. And if it tells you the population standard deviation, that's whenever you use Z. So the reason why I say that is because on the notes, it's somewhat easier because they separate it, you know, and then whenever it's on the homework, whenever it's on the test, it's all going to be together as one. So at least you have, we'll see some more examples, but I just wanted, again, your questions, you guys emailing me questions really helps me to help you guys better whenever I come to class. I know kind of what to explain better. So I got a couple emails about that. So anyways, 8.4. Interval estimation for population proportions. So it's the last thing we're talking about with proportions. Remember, proportions are, they give us a percentage, and this is for large samples. So the standard deviation of the sampling distribution of a sample proportion is the square root of p hat times q hat all over n. Again, our error is our z value times that sampling standard deviation. So it's, again, the same concept over and over and over, but instead of x bar, we have our proportion, which is p hat. So it's very similar than what we did to test 3. So confidence interval for a proportion at the 1 minus alpha percentage level is p hat plus or minus z times the sampling standard deviation. The value of z is found on the z chart, on the z table, for the given its confidence level, where the table that we made from before. And I'll go back to show you that. So let's do an example. Let's say that 44% of a sample of 1,000 people say religion is very important to them. So part A, find the point estimate for the population proportion. So they tell us 44% of people. This is going to be our p hat. P is the same thing as p hat, just like we said mu is the same thing as x bar. So we know that is 44%, which we are going to move the decimal 2 places to the left, and that will give us 0.44. Q hat is, we know, 1 minus p hat. So 1 minus 0.44. Going to our calculator, 1 minus 0.44 will give us 0.56. So I forgot to, whenever I type this out, I forgot to say that we're going to use a 99% confidence interval. So if we use 99% confidence, let's go back to that table that we used at the beginning of chapter 8. I'll pull it up right here for you. This was the table that we found at the beginning, saying if we're 99% confident, we're going to have a z table, a z value of 2.58. 2.58. And we got that from our confidence level table on, I believe it was page 2. Yep. On page 2. So we can use this to find our sampling standard deviation, the square root of p hat times q hat all over n. So the square root, p hat is 0.44, q hat is 0.56, all over n, which is 1,000. Plugging this straight into our calculator, the square root of 0.44 times 0.56 divided by 1,000. Boom, 0.015697. Again, I just want to kind of write out enough so that way rounding won't mess me up. I want to write out enough decimals so that way rounding won't mess me up. That's part A. Part B says we're going to use all of this stuff to find our margin of error, just like we've been doing. Oh, right here I put at the 99% confidence level. So I took this to go up here. The first example, I just wanted to break it down and kind of see everything. Usually they just give you, here's the problem, go. They don't break it down for you. So we know our error from up here is z times our sampling standard deviation, which we already found. So E is z times S sub p hat. Z was 2.58 times 0.015697. already have this S sub p hat in my calculator, so I just want to multiply that, so times 2.58, so that way there's no rounding, I have to plug it back in. We get 0.04049 is going to round up to 5. So we found our error. And then last but not least, finding our confidence level, our confidence interval. Construct the confidence interval at the 99% confidence level. So we know this is going to be p hat plus or minus our error, just like we did before we had x bar plus or minus our error. Our p hat is 0.44 plus or minus our error is 0.0405. Which is going to give us 0.44 minus 0.0405. Our lower limit's going to be 0.3995. Our upper limit is going to be second enter, the same thing but adding. And we get 0.4805. And that's going to be our confidence interval. Now for these, because we talked about percentages, sometimes, so make sure you read the directions, they want you to put it as percentages again. So or 39.95%, which is about 40%, to 48.05%, which is 48%. So sometimes they want it back because up here they gave it to you in percentages, we turn it into a decimal. So a lot of times they want you to take your answer and then turn your answer, because they gave it to you in percentages, they want your answer back in percentages. So or 40% to 48%. So again, remember to kind of put it back in English. They said, okay, they took a sample of 1,000 people and that sample had an average of 44%. It's saying we are 99% confident that everyone, the population, everyone would be between 40% and 48%. So we're taking that 1,000 people and we're trying to generalize it to everyone. So questions, comments, concerns on this first example. We're going to do another example just like it. But questions, comments, concerns on this one, please.
For the 48, don't we usually round up?
That's only for, so it should be 48.05. We round up whenever we're finding n, which is what we're going to be doing next. So good segue into the next thing. But only when you find n do you round up no matter what. Great question. Thank you. Any other questions? All right, so let's do the next example. This time our n is 20,000. Our p hat is 0.63. That means our q hat is 1 minus p hat. So 1 minus 0.63. And we get 0.37. Our sampling standard deviation is the square root of p hat, which is 0.63, times q hat, which is 0.37, all over n, which is 20,000. So putting that into our calculator just like we see it. We get 0. Uh-oh, this was, I put extra, it's okay. I put an extra 0. It's supposed to be 2,000, but 0.00, we'll just keep rolling with it. 34. 0.0034. So it asks us, what is Z for the 97% confidence level? All right, so let's go back to our table on page 2. 97%, 2.17, boom. 2.17, and that is from the table on page 2. What is the margin of error? We know the margin of error is z times our sampling standard deviation. So 2.17 times 0.0034, which is already in my calculator. So second answer, there we go, times our 2.17. So we should get 0.0074. So finding our confidence interval, we know is p hat plus or minus our error. Our p hat we said was 0.63 plus or minus our error, which is 0.0074. Our lower limit is 0.63 minus 0.0074, 0.6226. And then 0.63 plus 0.0074 will give us our upper limit of 0.6374. So that could be our answer. If they want it back in percentages, we can move the decimal 2 places to the right and get 62.26% to 63.74%. We're saying it's in between those two boundaries. And that's it for that example. We're going to do one more, like learning one more thing, which we kind of already talked about, is the n value. But before we go there, questions on this example before we go to finding n? Questions, comments, concerns for me? All right, so find a sampling size, so find n, given the margin of error, the sampling proportion, and the confidence level. So again, working backwards, we have this formula. That we are going to use. Going to our formula sheet. It is on our formula sheet, so don't worry about memorizing something crazy like this. Find the sample size, so we're going to find n. Needed for our error of 0.03, a p hat of 0.32, and a confidence level of 99%. Well, we know if confidence level is 99%, let's look at our table 2, page 2 table. Our z value is going to be 2.58 for 99%. And as you can see, it's like a lot of the same numbers over and over and over. So you kind of memorize them automatically from doing so many examples. So now we have everything we need, just plug it in. So n equals z squared times p hat times q hat all over our errors squared. So our z value is 2.58 squared times p hat, which is 0.32. That means our q hat, by the way, 1 minus p hat, so 1 minus 0.32. What did you say it was? 0.68?
Just like, wait, we didn't find Q.
Oh, sorry. I thought you were telling me the answer. I was like, oh, wow, thanks. I need to write faster then. That's what you're thinking? No, you're like, slow down.
Let's go.
Yeah. All right, so 0.68 all over e squared, which is 0.03 squared. There's just a lot going on. All you have to do is plug this into our calculator, though, and it will do all of that for us. So, trying to leave both things here. So up top we have 2.58 squared times 0.32 times 0.68 divided by 0.03 squared. And we get 1609.3. Now here, because we were talking about n, this is what we were talking about. Because we talked about n, we always round up no matter what. So even though it's 0.3, you always round up because we're talking about people on a sample size, so you can't have 0.3 of a person, so you always round it up. So if we get 1609.3696, we always round up to 1610. We always round up whenever we find n. To find n, we always round up. And we have one more page for chapter 8. Before we go there, kind of bringing it all together, before we go there, questions, comments, concerns for me. So this last page, what I did was, again, I went through all our notes, and then I went back through the homework and the quizzes, and I said, okay, what are we missing? What do we kind of need more of, in my opinion? And if you guys find more, please let me know, and I'll always add to it. But this was some things that I kind of wanted to touch base on. So our first example, given that n is 275 and p hat is 0.25, is the sample big enough to use a normal distribution to make a confidence interval for p? So remember, our rule for this is n times p hat has to be greater than 5, and, don't forget the n times q hat is also greater than 5. So we know p hat, let's go ahead and find q hat, which is 1 minus p hat, so 1 minus 0.25, which is 0.75. So we have 275, which is n, times p hat, which is 0.25. Is that bigger than 5? Do we have enough in our sample to be able to make a generalization? Yes, we do. That's 68.75, which is obviously bigger than 5. So that works. Let's do the same thing for q hat. So n, which is 275, times q hat, which is 0.75. Is that bigger than 5? And yes, again, we get 206.25, which is greater than 5. So our answer is yes, because it worked for both. If it did not work for either one, our answer would be no. So I kind of just wanted to drive that home. So before we go to the next example, questions on this one? Sorry, I keep bringing my hand over, making sure it's still recording. I still see people coughing, so I'll give you another minute before we go to the next example. Alrighty, so next example says, what is the sample size? So we're trying to find n, a conservative estimate. They use that word sometimes, so I wanted to make sure you realize this. It's the same thing. What is the sample size? What is the conservative estimate? We're still just trying to find n. That would limit the margin of error to within 0.27 of the population proportion for a 95% confidence interval, rounds to the nearest whole number. Note, when p hat and q hat are values are not known, we're going to use 0.5 for each when determining the sample size n. This is what's called the conservative estimate. So notice, they told us the error, they told us the confidence level, but they didn't tell us p hat. They didn't tell us q hat. So we're going to always know that if, okay, p hat is 0.5, q hat is 0.5. So our p hat is going to be 0.5. Q hat is still 0.5 because no p hat or q hat was given. They told us our margin of error was that 0.27, and they told us we had a 95% confidence level. So going to that table on page 2, real quick, 95% will give us 1.96. Bingo. table on page 2. So again, we're trying to find the sample size, so we're trying to find n. So we have that formula that we just used on the previous page, n equals z squared times p hat times q hat all over error squared. So z was 1.96 squared times p hat was 0.5 times q hat, which was also 0.5, all over our error, which is 0.27 squared. Plugging this into our calculator exactly like we see it. We get 13.174, blah, blah, blah. Remember, we're talking about n, we always round up. So even though it's 13.1, we know that n is 14. Again, we're going to always round up to our next whole number when finding n. So it's only when finding n and every time that we find n that we round up like that. We have one more example for chapter 8 before we go to chapter 9. Questions, comments, concerns on that before we do so? So next example, I'm going to leave this right here. But a sample of 557 observations taken from a population produced a sample proportion of 0.28. Make a 90% confidence interval for P. So let's put it all together and let's find a confidence interval. So it tells us a sample of 557. So our n value, our sample size is 557. Our sample proportion, which is P hat, is 0.28. That means we can find our Q hat is 1 minus P hat is 1 minus 0.28, which is 0.72. We know we are 90% confident, so using 90% confident on our table from page 2, we get 1.64 for our z value. So let's go ahead and find our confidence interval. By the way, we also have to find S sub P hat. Let's go ahead and just do it over here. The square root of P hat times Q hat all over n. So the square root of 0.28 times Q hat, which is 0.72, all over 557. All right, so our confidence interval. Again, I want to make sure that you're ready for the test. So on our formula sheet, it says the confidence interval is P hat plus or minus Z times S sub P hat. We already found S sub P hat, and it gives us that formula as well. So I want to just make sure to use exactly how it is on the formula sheet. So P hat is 0.28 plus or minus Z, which was 1.64, times our sampling standard deviation, which is the square root of 0.28 times 0.72, all over 557. And then we can break this up and say our lower bound.
So we don't have to find the answer. Like, it would be easier to find.
That's fine. Yeah, if you want to.
Okay.
The reason why I don't do it is because I don't.
It's going to be around a number.
Yeah,
Okay.
exactly. It's going to be a round number, and I don't want to round anything, so I just like to plug it all in at once. and then I can do my second enter thing, and then I can just use the same thing. I don't only plug everything in on one time. So the lower limit, the lower bound is 0.28 minus that stuff. And then our upper limit is going to be the same thing, but plus. Again, I'm just writing it for our notes. You probably wouldn't write this whole thing out if you don't want to. But I just want to make sure that you realize how we're getting everything. And then now just plugging it in. 0.28 minus 1.64 times the square root of 0.28 times 0.72 divided by 557. Zero 0.24879 is going to round up to 8. And then second enter, scrolling over, changing that minus to a plus. We get our upper boundary, 0.31120. So our interval is from 0.2488 to 0.3112. Again, if they want it in decimal form, if they want it in percent form, just move the decimal 2 times the rate. And I'll give you 24.88% to 31.12%. Either way, same answer, just depending on how Wiley Plus wants it, or the test. Remember, the test is going to be multiple choice. This question gave it to us in decimal form, so it probably wants the answer in decimal form. Is usually a good rule of thumb. If the question gives it to you in percent, they usually want percent. If they give it to you in decimal, they usually want decimal. Last but not least is the true proportion. So the true answer, we use this to generalize the answer, but it's telling us the true proportion, the true answer is 0.25. Is this in this confidence interval? Well, yes, 0.25 is between 0.2488 and 0.3112. So yes, because 0.25 is between 0.2488 and 0.3112. And that is it for our Chapter 8 notes.